In section 2.3, we look at the application of differential equations, and that being exponential growth and decay problems. In Pre-Calc 30, you may have used these equations when studying exponential growth and decay in Chapter 8. Notice in this first equation, we're talking about exponential growth, and how do we know that? Because our exponent, which is t over d, is a positive exponent, and in the second equation, exponential decay, our exponent is negative, which will indicate we have decay going on. The law of exponential change says, suppose we are interested in a quantity y that increases or decreases at a rate proportional to the present amount. Anytime we see that phrase, proportional to the present amount, we know that we are dealing with exponential growth and decay. Now, the differential equation that relates to exponential growth and decay is given by this differential equation right here. Anytime the variable on the right side of the equation is being multiplied by a constant, and that variable is the same as the variable in the top of our derivative, we know that this is the differential form of an exponential growth or decay question. Now, if we take this equation, dy dt equals ky, and we separate the variables like we did before in the last section, so I'm going to have dy over y is equal to k times dt, and now we're going to integrate both sides, so I get ln, the absolute value of y, is going to equal kt plus a constant. Now, remember, I'm trying to solve for y, so I have to exponentiate both sides to the base e. And again, e ln absolute y, we know, will change into absolute y. And e raised to the kt plus c, using our laws of exponents, is really e raised to the kt times e to the c. Now, e is a constant, and so too c is a constant. And remember, we said let plus or minus e to the c equals some other constant a, and that will eliminate the absolute value signs on the left-hand side of our equation because we've taken the plus or minus into account with our constant a. So therefore, we get an equation y equals a multiplied by e raised to the kt. Now we're going to use our initial condition, which says at time 0, y equals y subscript o. So in place of y, I'm putting y subscript o when t is equal to 0. So this part right here becomes e to the 0, which is 1. So therefore, y subscript o is just a. And therefore, my final equation is y equals y subscript o e to the kt. And this is the equation of exponential growth and decay. Now, if our k value is positive, so if k is greater than 0, we're going to get exponential growth. And if k is less than 0, we're going to get exponential decay. So this equation is very similar to these two equations. The only difference is now we're using the base e, which is a little bit more accurate than the base 2, and we just have to look at k to determine whether we're dealing with exponential growth or decay. Let's look at a few examples. The change n in the bacteria, number of bacteria in a cultured dish at time t is given by this differential equation. If n is equal to 3 when time is 0, find the approximate value of t when the total number of cells is 1210. Well, there's a couple ways we could do this problem. We could take the original differential equation and we could separate the variables, use our initial condition, and develop our equation. But by looking at the differential equation right away and seeing that n here is the same as here, and this is changing with respect to time, this is the differential equation for an equation of this form. Now, because we're talking about the number of cells n, they might change y into n, which really doesn't matter. It's just a change in variable. And this number 2 is k, so I know that my exponent now is 2t, and this guy right here tells me when time is 0, the number of cells is 3. That's really my initial number of cells. So my equation is n equals 3 e to the 2t. So this is the equation that I'm going to use for this problem. Now, we are asked to find t when the total number of cells is 1210. So at this point, I just plug 1210 in for the n, and I'm going to solve for t. So first things first, I have to divide both sides by 3. So I'll be left with 1210 divided by 3 is equal to e to the 2t. And just like before, when I'm trying to solve an exponential equation, I need to take the logarithm of both sides. So the logarithm of 1210 divided by 3 is going to equal, whoops, I'm just going to try to undo that mess there a bit. 1210 divided by 3 is equal to the logarithm of e to the 2t. And remember, ln 2t, the 2t can come out front, and ln e is equal to 1, so we can drop that. And my left side is not going to change. And now all I have to do is divide both sides by 2 or times the left side by 1/2. And if I do that, I will get my final answer. So I'm just going to try to erase this here. And that 2 will be gone. So that's going to be the time that the number of cells will grow to 1210. Now, if we take out our calculator and we punch that into our calculator, you're going to go the natural logarithm of 1210 divided by 3, and then times that by 0.5. It works out to be approximately 2.9998 is equal to time, which is going to be approximately 3. Now, it doesn't give us a unit for our time, so we just leave our time as 3. Okay, let's take a look at another problem. This question says a colony of bacteria grow under ideal conditions exponentially with time. At the end of 7 hours, there are 15,000 bacteria, so that's important information for us. And at the end of 12 hours, there are 28,000 bacteria present. The question is, how many bacteria are there or were there initially? Now, it's telling us it's growing exponentially with time, so we know this is an exponential growth equation, so we can go straight to our formula, y equals yo e raised to the kt. And using our first set of data, we know that when time is 7, the total number of bacteria is 1,500, so 15,000, sorry, is going to be equal to y subscript o e raised to the 7k. Now, using our second set of data, we can use the same formula that we can start with the same formula. And we know that in 12 hours, the total number of bacteria is 28,000. So that becomes 12k. So now we're down to 2 equations with 2 unknowns. So therefore, we can solve for our unknowns. And our goal is at the end to figure out how many there were initially, which is our y subscript o, our initial amount. So in each of these equations, the easiest term to isolate would be y subscript o. So I'm going to divide the 15,000 by e to the 7k. And I'm going to divide the 28,000 on the right-hand side here. Let me just change my color. By e to the 12k. Now, if y subscript o is equal to this, and y subscript o equals this, those two things have to equal each other. So 15,000 divided by e to the 7k has to equal 28,000 divided by e to the 12k. Now I'm going to do some across multiplying or manipulating, I'm going to move the e to the 12k up there and the 15,000 down there. So I'm going to get e to the 12k divided by e to the 7k is equal to 28,000 over 15,000. So the zeros will cancel. Using my laws of exponents, if my bases are the same, I can subtract my exponents. So therefore, I'm going to get e to the 12k minus 7k is going to be e to the 5k is equal to 28 over 15. And again, to get rid of, or to solve the exponential equation, I need to take the logarithm of both sides. So we'll take the log of both sides. So ln of e to the 5k is going to be ln of 28 over 15. The 5k will come out front, and ln e is equal to 1. And now divide by 5 or times by 1/5. So k is going to be 1/5 ln 28 divided by 15. So there's your value of k. So now that I know k, I can go back to either of these two equations here to find y subscript o. So I'm going to take my first equation in red that said y subscript o was equal to 15,000 divided by e, and that was to the 7k, so it's going to be 7, and in place of k, I'm going to put that ugly mess in there, which will be 1/5 ln 28 over 15. And now it's just a matter of plugging this into your calculator. Now the hardest part is going to be to figure out that exponent. So if we figure that out, let's just do this together. So if you get out your calculator, I would do ln of 28 divided by 15 first. Hit enter on your calculator. I get 0.624. Then I'm going to times that by 7 over 5. So times it by 7 divided by 5, and that's 0.873816. Now I need to raise that as an exponent to the base e. So on your calculator again, you can go e raised to that previous answer. And when I take e to the 0.8738, I get 2.396. And then 15,000 divided by 2.396 works out to be equal to 6,260.338 if we round up number of cells that there were, or bacteria there were initially. And if you look at our data, that seems to make sense. There were 15,000 after 7 hours. There was 28,000 after 12 hours. If my initial amount would have been greater than 15,000, you obviously know you made a mistake, but that seems to be an acceptable solution to the problem. Okay, let's try another example. This one here is talking about the concentration of medication injected into a bloodstream, and it drops at a rate proportional to the existing concentration. So again, it is dropping at a rate proportional to the existing concentration or the original amount. So this again is an exponential decay. And how do we know it's decay? Because it's dropping. So we're going to be using the formula again, y equals y subscript o e raised to the kt, and this time we're going to put a negative with the k because it's exponential decay. I'm assuming you guys have already figured out that y subscript o stands for the original amount and y is the final amount. I forgot to explain that clearly at the very beginning, but I apologize for that, but it should make sense now. So if we take a look at the remaining part of the question, it says if the factor of proportionality is 30% per hour, so this is my factor of proportionality, which is my constant k. So k we know is 0.30. In how many hours, so we're looking for the time, will the concentration be 1/10 of the initial concentration? So the final amount is going to be 1/10 of the initial amount. So it really doesn't matter what I select my initial amount to be. The final amount is 1/10 of it. So it would make sense if I let my initial amount be, say, 10, and my final amount is 1/10 of the original. So now we're going to plug this information into my equation. So I'm going to get 1 is equal to 10 e to the negative 0.30 times t. Again, the first thing you need to do is divide the 10 over. The biggest mistake is to multiply the 10 and the e, which is wrong. So you can get 1 divided by 10, which is 0.1, is equal to e to negative 0.30 t. Again, I take the log of 0.1 is equal to ln of e to the negative 0.30 t. And again, that exponent comes out front. And now I divide both sides by negative 0.30. Now some of you might be saying, well, on the left I have a positive number divided by a negative, and time has to be positive. But remember, when you're taking the logarithm of a number that is less than 1, this ln 0.1 is negative. So if you go to your calculator and you type in ln 0.1, and then divide that by negative 0.3, you should get a time of 7.675 hours. So 7.675 hours is equal to time. So that would be the amount of time it would take for this medication to decrease to 1/10 of its initial amount. Okay, this one here is slightly different because they give us a different differential equation. But again, we can use our separation of the variables here. So this question says a cup of coffee at 180 degrees Celsius, or Fahrenheit, is placed on a table in a room at 68 degrees Fahrenheit. The differential equation for its temperature at time t is given by the following. With this initial condition, okay, after 10 minutes, what is the temperature of the coffee? So that's what we're looking for in the end. So let's start by separating the variables here. So in this particular case, I'm going to divide dy by y minus 68, and that is going to equal negative 0.11 dt. Now we're going to integrate both sides like we did before, so I get ln, the absolute value of y minus 68, is going to be equal to negative 0.11 t, and then plus our constant. And as we said before, it's sometimes easier to get rid of the logarithm first by exponentiating both sides to the base e. So the left-hand side will become the absolute value of y minus 68 is equal to e to the negative 0.11 t times e to the c. Again, we'll make our statement. Plus or minus e to the c is equal to some other constant a. So therefore, my equation becomes y minus 68 is equal to a e to the negative 0.11 t. Now I can use my initial condition right here to solve for a, my constant. So it tells me that at time 0, the final temperature is 180. So 180 minus 68 is equal to a e to the negative 0.11 times 0. We know that this quantity here becomes 1, and therefore 180 minus 68 is going to be my answer for my constant a. So if I work that out, 180 minus 68, that works out to be 112. So therefore, my equation now will be, I'm going to start a new page here. My equation is going to be y minus 68 is 112 e raised to the negative 0.11 t. Negative point, oh shoot, sorry about that. This is getting frustrating, this pen. Try that again. Negative 0.11 t. Oh, wow. Okay, so now let's answer the question. The question was asking us, after 10 minutes, find the temperature of the coffee. Well, now I just plug a 10 in for t, and I work this out. So y minus 68 is going to be 112 e to the negative 0.11 times 10. And if I evaluate the right-hand side, I'm going to get e raised to the negative 1.1 when I multiply these two exponents together. And that gives me an answer of 0.3328. Times that by 112, and I get 37. And then I add 68 to that, and my final answer is 105.281 degrees Celsius. So that would be my answer to this problem. So again, this is a differential equation that we have to separate the variables. Slightly different than the exponential growth and decay, but just another application of separable differential equations. Okay, let's get back to some more exponential growth and decay problems. So this one states that the population grows according to this equation. And again, this is a differential equation for exponential growth and decay. And it tells me that the population doubles every 10 years, and they want us to find the value of k. So again, we know it's exponential growth because it tells us that in the problem. So we know we can start with this equation right here. Y equals yo e to the kt. And let's punch in or plug in the information we know. Okay, we know that the population doubles every 10 years. So no matter what our original amount is, so say we say it's 1, our final amount will be 2 when the time is 10 years. So I'll plug a 2 in for y, a 1 in for the original, and this is going to be e raised to the 10 times k. And now the 1 is irrelevant. We can lose that. Take the logarithm of both sides, and we end up with that. Now I can bring my exponent out front. ln e is equal to 1, so I don't need to worry about it. And now I'm going to divide this whole thing by 10, and that's what my value of k is. So again, that question was pretty straightforward. Again, they don't give us the initial and final populations, but they give us a ratio. They tell us it doubles. So whatever you choose for the original population, you just double it for the final population. In our next example, we look at the value of a computer decreasing at a rate proportional to its current value or initial value. And in this question, it tells us that the computer was worth $850 initially, and it is worth $306 after 2 years. And they want to know how much the computer will be worth after 5 years. So again, because it's talking about proportionality, it's decreasing at a rate at any time in relation to the value of the computer. This is exponential decay, so therefore we're going to use our exponential decay formula with k being negative. Again, we'll use this provided information here to help us find the value of k, and then we will use that to help us answer the question as to how much the computer will be worth after 5 years. So I know that initially my computer was $850, and it says that the time was 2 years, so t will be 2, and the final amount of the computer was $306. So again, we're going to have to divide both sides by 850. So I'm going to have 306 divided by 850 is going to equal e to the negative 2k. And if I take the logarithm of both sides, so I get ln of 306 over 850, and I could probably reduce that. So 306 divided by 850, and if I convert to a fraction, it's 9 over 25 is going to equal, when I take the logarithm of the right-hand side, the negative 2k comes out front, and the ln becomes 1, so it drops off. And now I divide this side by negative 2, and I end up getting my answer for k to be, if I want to write it as a fraction out front, negative 1/2 ln of 9 over 25 is equal to k. So now I can rewrite my equation. I know my initial amount, I know my value of k, and now I can solve for how much the computer will be worth after 5 years. So I have y is equal to, my initial amount is 850, k, well, I have a negative in my equation and a negative out here, so that's going to turn out to be 1/2 ln 9 over 25, which is my negative amount because the logarithm is of a number less than 1 is negative, and I'm timesing that whole thing by 5. Now be careful that you don't include the 5 with the logarithm when you evaluate the exponent. So let's evaluate the exponent first. So it's going to be the natural logarithm of 9 divided by 25. I'm going to multiply that by 5, and then I'm going to times that by 0.5, which is 1/2. And I end up getting an exponent of negative 2.5541. So 850 e raised to the negative 2.5541. And again, you wouldn't round off. You could carry that right through to the final answer before you round off, but I'm just showing you my work here. So this is 5, 5, 4, etc. So if I take e and I raise it to that exponent, and I times it by 850, it tells me that the computer will be worth approximately $66.10 if I round off to 2 decimal places. So your computer's not going to be worth very much after 5 years. In our last section dealing with exponential growth and decay, we're going to look at Newton's law of cooling. And Newton's law of cooling says that the rate of cooling an object is proportional to the temperature difference between the object and its surroundings, provided the difference is not too large. And this also applies to if an object is warming up as opposed to cooling down. So the temperature T is the temperature of the object at time t, and Ts is the temperature of the surroundings. So this is the differential equation, and we end up getting, if we separate the variables and integrate, we end up getting this as our exponential equation. Now there is a mistake in here, and I'll change it here briefly. This should be T subscript S. So the T, which is the temperature, minus the temperature of the surroundings is equal to the original temperature minus the temperature of the surroundings times e to the negative kt. So let's take a look at an example here, and I'm just going to start over here. So let me get rid of this. And in this example, it talks about a object at 80 degrees Celsius is placed in a room at 20. After 2 minutes, the object is cooled to 60. How many minutes will it take for the temperature to reach 40? So let's start off with what we know. Okay, originally we know that our object was at 80 degrees Celsius. And then the temperature of the surroundings was equal to 20 degrees Celsius. After 2 minutes, it says that the object had cooled to 60 degrees, so that's my final temperature. And the time it took this to happen was 2 minutes. So if we take a look at our equation, which once we corrected it, it said it is T minus T subscript S equals T subscript O minus T subscript S. E raised to, now some people will put the negative up top if it's cooling. It really doesn't matter because it'll all work out in the end, but we'll put it in there. So it's e to the negative kt because we know it's cooling. So let's plug in our information. So we know that this is 60 minus 20 is equal to 80 minus 20 e to the negative k times 2. So my left-hand side works out to be 40 60e to the negative 2k. Divide by 60 and reduce, and this is going to be 2/3 is equal to e to the negative 2k. Take the logarithm of both sides, so ln 2/3 is going to equal negative 2k. And if I bring the negative 1/2 to the other side by dividing, that's what k is equal to. So if you notice, this actual answer would be a positive value because ln 2/3 is negative times a negative, but when I plug it back into my equation, it would be a negative up there. And if I didn't have a negative in the original, this would have worked out to be a negative answer, and it still would have worked out to be negative in the equation. So it really doesn't matter how you settle up, it all works out to be the same. So now we know the value of k, so let's plug that back in. So I'm going to have t minus t subscript s is equal to the original amount minus t subscript s times e raised to the negative 1/2 ln 2/3 times t. So I found the value of k. Now let's try to figure out how long it's going to take for it to reach 40 degrees Celsius. Okay, so again, we'll start with the temperature that we want to end up with. We want to get to 40 minus the temperature of the surroundings, and the temperature of the surroundings was 20 is equal to the original temperature minus the temperature of the surroundings. And this is going to be e to the, let's just figure out that negative 1/2 ln 2/3 right away. So should be actually a negative of all of that. So negative 0.5 times ln 2 divided by 3. So this ends up being negative 0.2027 t. Okay, so there's my equation. So I got to figure this out. So this is going to be 20. The right-hand side will be 60 e raised to the negative 0.2027 t. Divide by 60, which will make this 1/3, is equal to e to the negative 0.2027 t. Take the logarithm of both sides. And when I take the logarithm of the right side, we should know by now that this is just going to come out front. And now I'm going to divide by negative 0.2027, and that should give me t. So ln of 1 divided by 3 divided by negative 0.2027 works out to be approximately 5.4198 minutes is equal to t. And that kind of makes sense. If it cools down to 60 degrees in 2 minutes, it's going to take a bit longer to get down to 40 degrees. So a total of 5.41 does seem to make sense in this question. Okay, we have another example we can look at using the law of cooling. This one here says that a thermometer is taken from an inside room and placed outside where the air temperature is 5 degrees. After 1 minute, the thermometer reads 55 degrees Fahrenheit. After 5 minutes, the thermometer reads 30 degrees Fahrenheit. What is the initial temperature of the room? So again, let's take a look at what we're given. Okay, the thermometer is taken from inside a room and placed outside where the air temperature is 5 degrees Fahrenheit. So the temperature of the surroundings is 5 degrees Fahrenheit. Our time is 1 minute. And it says the temperature reads, after 1 minute, the temperature reads 55 degrees Fahrenheit. and we're trying to figure out what the initial temperature of the room is. Okay, so given our first set of data, okay, we can plug our information into our formula. T minus Ts is equal to To minus Ts times e to the kt. Okay, so if we take a look at, we're looking for TO, and we know that the temperature after 1 minute was 55 degrees, and the temperature of the surroundings was 5. TO was what we're looking for, minus 5, which was the temperature of the surroundings, is e to the 1k, because the time is 1 minute. Okay, I could also use the other information that says after 5 minutes, the temperature, that should say reads 30 degrees. So when T is equal to 5, the temperature is 30 degrees Fahrenheit. So therefore, using the same formula, which is T minus Ts is equal to To minus Ts e to the kt. Okay, we know the temperature now is 30 minus the temperature of the surroundings is 5 is equal to T minus 5, and this is going to be e raised to the time is 5 minutes, so it's going to be 5k. So now you notice I have TO minus 5 here and TO minus 5 here. So again, I have two equations with two unknowns. So I can solve for K first and then go back and find the original temperature of the object. So I'm going to isolate the TO minus 5 on both sides. So on my blue equation, I am going to end up getting 55 minus 5 obviously is 50 divided by e to the 1k equals TO minus 5. And in my red equation, I'm going to get 25 divided by e to the 5k is equal to TO minus 5. So since this equals TO minus 5 and so does this, these two things have to equal each other. So let's do that. If I equate those, 50 over e to the k is equal to 25 over e to the 5k. If I do some fancy cross multiplying, I'm going to get e to the 5k over e to the 1k is equal to 25 over 50. Using my laws of exponents, 5k minus 1k is going to give me e to the 4k is equal to 1/2. Now I take the logarithm of both sides, and 4k is going to be ln of 1/2, and therefore k is going to be 1/4 times ln of 1/2. So I figured out the value of k. So now we can just go back to either here or here and figure out what the original temperature is. So let's do that. So I'll use the one on the left here, so 50 divided by E and K, we said was 1/4 ln 1/2. So 1/4 times ln 1/2. And this equaled T subscript O minus 5. So if I figure out the left-hand side, again, let's do the exponent first. So ln of 1/2 times 1/4, and I get 50 over e to the negative. And again, we wouldn't round off, but I'm just showing you the calculations, is equal to TO minus 5. So 50 divided by e to the negative 0.17 is negative 2. that can't be right here. 50 divided by e raised to the negative 0.173 is 59.44. And now I just add 5 over, and the original temperature of my object is approximately that many degrees Fahrenheit. So again, that was a pretty tough problem. We had to take the two sets of information and set up two equations with two unknowns, solve for K, and then go back and find our original amount. Or original temperature, sorry. Okay, let's take a look at this last example, and I think that'll be it for this lesson. This lesson's got a little longer than I'd hoped. And this one's talking about half-life of radioactive substance, and the half-life H is given by ln over K. And it says the half-life of a radioactive substance is the time required for a radioactive element to decay to half its original amount. It's a scientists who do carbon-14 dating use 5,700 years for its half-life. Find the age of a sample of which 10% of radioactive material originally present has decayed. Okay, so again, we know this is exponential decay, so we're going to be dealing with the formula y equals yo e raised to the negative kt. Now the first thing we need to do is find the value of K. Well, we know the half-life right here is equal to ln 2 divided by K. So if we solve for K, K would equal ln 2 divided by the half-life, which in this case is 5,700 years. So that's my value of K. And it says we want to find the age of a sample. So we're looking for the time is our question mark. In which 10% of the radioactive material originally present has decayed. So 10% has decayed, which means if my original amount was 1, 10% has decayed, my final amount is going to be 0.9. So therefore I plug in my information. So y is going to be 0.9 is equal to 1, e raised to the negative ln 2 over 5,700 t. And now I take the logarithm of both sides because dividing by the 1 here is irrelevant, so the 1 cancels out. So ln of 0.9 is going to equal ln of the right, this negative ln 2 over 5,700 t. And now all I'm going to do is divide ln 2 divided by 5,700 to the other side. So negative ln 2 divided by 5,700. And this should give you the approximate age of the carbon-14. So if I work this out, I get ln 0.9 divided by negative ln 2 divided by 5,700, and this works out to be approximately 866 years is going to be how old the age of the sample is. So again, this question is very similar. The only difference was to find K, you had to take the half-life and evaluate K using the half-life equals ln 2 over K. So that is the end of exponential growth and decay. Now, I know this lesson seemed long. Fortunately, there's not that much of this content that shows up on the AP exam. Definitely separation of the variables and separating differential equations shows up, but not so much the exponential growth and decay. So we'll look at more of these when we review, but your assignment from your textbook is as follows. So there it is. Give it a whirl, see how you do, and feel free to email me if you have any questions.